Given that g of x is equal to x squared plus 16 over x, find any local max and min values of g using the second derivative test. So again, what we're going to do is we're going to find the derivative, set it equal to 0 to find our critical numbers, and then determine whether or not we're looking at something that's concave up or concave down, and then from that decide whether or not it's a local max or a local min. So let's find our first derivative first. And the way we're going to do that is, well, let's rewrite g of x first. Let's rewrite this as, so this will be g of x is equal to x squared plus 16, and then I'm going to say x to the negative 1. Just make it a little easier to take the derivative of that. So now g prime of x, will be, so the 2 would come down, so we get 2x, and then this will be minus 16 x to the negative 2, right? Subtract 1. Or we could write it with without the negative exponent, so that'd be 2x minus 16 over x squared. So now from here, if we find our critical numbers, well, we want to make this equal to 0, right? And just notice when we make this equal to 0 that it's not exactly clear what would make x what would make this true, what would make this all equal to 0, right? If it was written in this form. So what we want to do is we want to make this all over a common denominator, so that we can just look at the numerator to see what will make it equal to 0. So what we're going to do is we're going to rewrite this as 0 is equal to, and then multiply the left term here by x squared, top and bottom. So we get 2x cubed minus 16 all over x squared. Hopefully you see that, right? I just went like x squared times x squared. That's where the x cubed came from. Okay, so now that is a bit better, right? Because now I can see, okay, whatever makes the numerator equal to 0 is going to make the whole thing 0. So I really just want to look at this and say, okay, 0 is equal to 2x cubed is equal to 16. I'm just going to forget about the denominator for a second, right? So from there, we're just going to, here, I'll carry on up here. So then bring 16 to the other side. So I get 16 is equal to 2x cubed. Divide by 2. So we get 8 is equal to x cubed. And then take the cube root. So we get x is equal to 2. All right, so we have a critical number of 2. Now, you might be saying, what about the denominator there, right? Because in other lessons, we were including the denominator as our critical number. And you can think of it as a critical number too, right? It could be 2 and 0. But just think about what that is, right? When you're dividing by 0, like in the original function, this one here, what that was an asymptote, right? Like when you actually graph this thing, that would be a line that it didn't cross, right? Maybe it does something like this. So there's no way that that's going to be a local max or a local min. It's not even in the domain of the original, right? So in that case, I don't have to worry about the denominator here. But that being said, just we could use that as a critical number if we were more interested in saying, okay, where is it increasing or where is it decreasing? Because those things around an asymptote, that will change, right? Maybe it's doing this and then decreasing here, or maybe it's increasing on this side and then it continues to increase on the other side, right? So it's just not interesting if I'm trying to figure out whether or not I'm dealing with a max or a min value, right? So that's only going to be at 2. Okay, hopefully that makes sense. Okay, so then from there, let's find our second derivative. So our first derivative was here or here, right? We can write it in either form. I might actually take the first one just because it's easier to take the derivative of, right? So if I take the derivative of this one here, so g double prime of x is equal to, so then this would become just 2, and then minus, oh, actually plus, right? Negative comes down, so plus 32 x to the negative 3. So now if we plug in for our second derivative, if we plug in our critical number of 2, then what we get is 2 plus 32 and then over 2 to the 3, right? I just rewrote this down on the bottom. Hopefully that didn't confuse you. And what we get is a second derivative equal to 6. Okay. So what's that telling us? So it's telling us that the second derivative at 2 is greater than 0. Therefore, we're dealing with a concave up scenario, which means you can say like therefore again if you like. Therefore, this is a local minimum. Has to be, because if it's concave up, then that's got to be the bottom right at that point, right? All right, so we've figured out what it is. The last thing to do here, let's actually figure out what the point itself is. We know the x value. We just need to know the y value. So going back to the original, we can say, okay, then g of 2 is equal to, and then that would be 2 squared plus 16 over 2. 2. So then g of 2 is equal to 12. So we have a point. So like therefore, we have a point at 2 comma 12. So now the question didn't ask us to graph it this time. And to tell you the truth is because we don't really have the skills to graph this thing yet. But to give you a point of like how that actually comes out, how that looks, it might be helpful to take a look at the graph here. So in this case, right, you can see there's that asymptote that we were talking about, right? That would have been my critical number of 0. So like I said, if we were interested in figuring out whether or not it was increasing on one side or decreasing on the other, right? Or decreasing and decreasing in this case, then you would have taken that critical number into account. But for us, we were only caring about where the local min was. So that ended up being right here on our graph.